Welcome to a course on sequence and series. In the previous lectures, we have seen the definition of a convergent sequence and properties of convergent sequences in a metric space. In this lecture, we are going to see algebra of convergent sequences. Okay, what do we mean by algebra of convergent sequences? That is, we are going to deal with the addition of convergent sequences and multiplication of convergent sequences, scalar multiplication, all those stuff we will see in this lecture. First, let us see what do we mean by algebra of convergent sequences. Suppose Sn is some sequence in a metric space X and Tn is some another metric space in Tn is some sequence in the same metric space, then Sn plus Tn, the sequence Sn plus Tn is defined in the way that term-wise addition. We will have to do a term-wise addition and then we will have to sum it up. This is how scalar multiplication of the sequences. Okay, this is nothing but the addition of two sequences is done in this way, right? And scalar multiplication of sequences is going to be done with term-wise. Similarly, if you are multiplying two sequences Sn and Tn, this is also what? A term-wise multiplication and inversion of the sequences. Thus, invert each term and make the sequence. Right? This is how we are going to perform the algebra of sequences, and the convergence of the original sequence implies the resultant or not. That is what we are going to see in this lecture. Here we are not going to talk these things in general. We are going to talk these things in the set of complex numbers, right? Whenever we are talking about set of complex numbers, that may be treated in two ways. That is simply a complex number or in a two-dimensional thing. That is, we may treat that in a two-dimensional plane. If suppose we treat a real sequence from the set of complex numbers, that means what? We are going to have a sequence with imaginary part 0, which means when we treat that in a plane, we'll have to take things only on the x-axis and we are not going for the imaginary axis. X-axis is treated as real axis and the y-axis is treated as imaginary axis, right? Now let us directly get into the hypothesis of the theorem. The statement you may see here. Here we are given that two sequences Sn and Tn are complex sequences, and Sn limit Sn is S and limit Tn is T. So this is the assumption that we make. Okay. Here it is given that Sn converges to S and the sequence Tn converges to T. With this we are going to prove the rest of the things. That is, first thing that we are trying to prove is limit Sn plus Tn. Okay, limit Sn plus Tn is S plus T. Okay, by the definition of a convergence, what do we have? There exists. Okay, first of all we will have to say something about the things, right? For every epsilon greater than 0, this epsilon is what? It is some negligible quantity. It can be anything, right? So there is no need to represent that by epsilon itself. It may be some combination of epsilon, simply epsilon square, epsilon upon 10, epsilon by 4 plus epsilon square plus epsilon cube. These kind of any value it may be there. It has to be some positive quantity and which has to be very, very small, right? That is the thing. For every epsilon greater than 0, there exists. Here let me take n1 and n2 because I am going to talk about two sequences, right? Such that here, since these are considered in complex, that is under standard Euclidean metric we are talking. Okay, We are not talking in any other metric. We are talking only in the standard Euclidean metric. Therefore, what will we have? We will have absolute of Sn minus S less than epsilon by 2. You may have it as simply epsilon. That is no bother. For the sake of simplicity purpose, I am taking it to be epsilon by 2. Right? And Tn minus T less than epsilon by 2. This is true for n bigger than or equals n1, and this is true for all n bigger than or equals n2. Okay. Now what am I going to do is that I am going to take n to be the maximum of n1, n2. Why we are taking maximum? Suppose, okay, my n1 is 10 power 15. Okay, my n2 is 10 power 16. Right? So between these and this, okay, this is the larger quantity. When something is true beyond this limit, it will also be true beyond this limit as well, because this is a greater quantity. After this value, this is true. Okay, but if you see in the range between these two values, you will notice that this will not hold true, because this is true only if n is bigger than or equals n2, which means after this stage only this is going to be true. After this stage, this is also true. That is why we are taking n to be the maximum of these two. Right? Now, let us consider for n bigger than or equals n. Okay, that is among these quantities, after the maximum stage, I am going to talk about these things. These are some examples that I have given. Okay, we don't know what is the bigger value among these two. That is why we are simply mentioning that to be the maximum of n1, n2. That is what we are taking as n. For n bigger than or equals n, consider absolute of Sn plus Tn minus S plus T. Because we are trying to prove limit n goes to infinity Sn plus Tn is S plus T, for which we need to consider this one, and we have to prove this quantity is, the difference between these two quantities, negligible. That is what we are going to prove. Now let me combine these things in this fashion. Okay, using triangle inequality, I am writing like this. And what is this? This is epsilon by 2, and this is epsilon by 2, and finally the resultant is going to be epsilon, which means what I have? I have Sn plus Tn minus S plus T, which is less than epsilon, which implies limit n goes to infinity Sn plus Tn is S plus T. Right? Suppose instead of taking epsilon by 2 here, epsilon by 2, suppose you take epsilon here, what is going to happen? Let us see that too. Okay, I am taking these two to be epsilon. So here I will have epsilon plus epsilon, which is 2 epsilon. Right? Here I will have 2 epsilon. Okay, epsilon is negligible quantity, which means you have around 10 power minus 24, 25, even 250 you may take. Okay, consider that sort of very small, even 10 power minus billion, that can be your epsilon. Okay, your epsilon is some negligible quantity. When you multiply 2 with that negligible quantity, it still remains a negligible quantity. Okay, you take it 10 power minus billion or 10 power minus billion upon 2, it doesn't bother, because these quantities are negligible. That is why it is no bother if you take epsilon or epsilon by 2 or whatever may be the things, right? So that is the idea behind this, the choice of epsilon, and the reason why we choose epsilon by 2 is to get epsilon here, because you don't get confused with the definition. Okay, now in the second part of this theorem, we are going to prove a scalar multiple of a sequence is convergent. Okay, that is, you may see it in the theorem statement. We are going to multiply a constant c with all the elements of the sequence, and we are going to check the convergence. Okay, so this is what we are trying to prove now. Okay, now again by the definition I am directly writing all those stuff. Here the metric is absolute, right? Standard Euclidean metric. Absolute of Sn minus S is less than epsilon. Supposing you don't know what to choose here, as of now have it as epsilon, and while proceeding you will have some result, right? With that result you may make changes here. Okay, so I'll tell you that idea as well by this. Okay, this is what I am going to have for all n bigger than or equals n. Fine. Now what am I going to do? I am going to consider absolute of Csn minus Cs. Okay, this is going to be, if I take C as a common thing, I have Sn minus S. Okay, and this still remains absolute of C, absolute of Sn minus S, and this is less than absolute of C times of, this is going to be epsilon. At the end, if you wish to have epsilon, what should be the case? You will have to divide this quantity by absolute of C, right? So take this to be epsilon upon absolute of C. So epsilon, which gives you what? Absolute of Csn minus Cs is less than epsilon. This tells you limit n tends to infinity, Csn is Cs. Right? So with the same idea, okay, the basic assumption is this. Now we are trying to prove a limit n tends to infinity, a constant added with all the terms of the sequence is going to be this. Okay, this is the second part of the second thing. Okay, here the assumption that I am going to have from the definition, I am going to have this, and consider what? Absolute of C plus Sn minus C plus S. So this is C plus Sn minus C minus S. C gets cancelled, so absolute of Sn minus S, which is less than epsilon, and this is proof. In the third part of this theorem, we are to prove the multiplication of sequences is convergent whenever the sequences are convergent. Here, with the assumption that Sn converges to S and Tn converges to T, we are going to prove this thing. For which, let us make use of the definition again. By the definition, what do we have? There exist n1 and n2 positive integers, right? These two are positive integers such that absolute of Sn minus S is less than epsilon for n bigger than or equals n1, and absolute of Tn minus T less than epsilon for n bigger than or equals n2. Okay, let us take n to be the maximum of n1 comma n2, and for n bigger than or equals n, consider the requirement, that is absolute of Sn minus absolute of Sn minus St is going to be what? I am going to add and subtract few terms so that the value is unaltered, but we are going to come to a required result, that is absolute of Sn minus Snt plus Snt, okay, plus Tns minus Tns plus St minus St, and we have this St. Okay, I have added and subtracted three terms so that the value is unaltered. Now I am going to do some stuff here. Absolute of, let me take Sn as a common thing, so Tn minus T from these two terms. Okay, now let me choose T as a common thing. So when I take T, what am I going to get from these two? Let me take from this two, absolute of Sn minus S. Okay, now let me take out minus S as a common thing minus s, let me take, so Tn, okay, from here I will have minus t, right, and I have these two things, that is absolute of sorry, I can take Sn as the common thing, so that I'll have Tn minus t. Okay, now if you see, you have Tn minus t as a common thing in these two things, or in these two things. Okay, so it is just a matter of convenience. Okay, you take whatever you want, Sn minus s, Tn minus t plus t times of Sn minus s minus s times of Tn minus t. This is what we have. Okay, so using the triangle inequality, absolute of Sn minus s, Tn minus t plus t times of absolute of Sn minus s, you may have absolute for this too, plus absolute of s into absolute of Tn minus t. Okay, and now what are you going to do? You are going to make the things happen. So you will have, for this you will have epsilon, and for this you will have epsilon, and what is going to happen here? Because of the convergence, you will have this to be absolute of t times of epsilon plus absolute of s times of epsilon, and you may see these epsilons are very negligible quantity, and finally what will you have? You will have another negligible quantity. That's it. Okay, just because the convergence is happening, you may also say what the thing. You may take this to be 0, this to be 0. When you make the limit as n approaches infinity, you will have this to be 0, this to be 0, and hence what happens? Absolute of Sn Tn converges to absolute St. Sorry, Sn Tn converges to St. That you will get. Okay, and this proves limit n tends to infinity Sn Tn as St. Okay, and in the fourth part we are about to prove the reciprocal of the convergence sequence. Terms in the convergence sequence also converges in the set of complex numbers under standard Euclidean metric. Okay, this is a quite tricky part, and let us explore that too. Okay, here what are we about to prove? We are about to prove limit n goes to infinity 1 upon Sn is 1 upon s. Okay, now what am I going to do is that I am going to choose some m such that absolute of Sn minus s is less than absolute of s upon 2. Is it possible? One may have to think, right? So in general, from this, using the triangle inequality, what may you write? You may write absolute of Sn plus absolute of s. This is a positive non-negative quantity, and this is also some non-negative quantity. So you have addition of two non-negative quantities. Okay, I am going to take only half of this, right? That is what I am going to take, and I am not saying this is true for all the values. This is going to be true after some stage only. That is what we are saying. So the choice is valid, right? After choosing this, what are we going to do? We are going to play with something. Okay, you have absolute of this thing, right? Using the property of the absolute, you may also write this to be absolute of s minus absolute of Sn. You may write it in either way. This is also just a matter of convenience. Okay, I am taking in this form, and now this tells you what absolute of s minus absolute of Sn is smaller than or equals absolute of Sn minus s, and this is less than absolute of s upon 2. So I am going to do what things? Okay, just compare these two things and take this to this side and bring this to this side. So you will have absolute of s minus absolute of s upon 2 is less than or equals absolute strictly less than, because we have strictly less than here, right? So absolute of Sn, and this gives you what? Your absolute of Sn. You have brought this to this side, right? So this is going to be bigger than absolute of S minus S upon 2, and this gives you 1 upon absolute of Sn is less than 2 upon absolute of S. Okay, you have this. Now we are going to make use of this thing, and by the definition you are going to have those things, right? Those stuff we will write by the definition of what? By the definition of convergent sequences, absolute of Sn minus absolute of S is less than epsilon, and you will have something, but we don't know what is that something. We are having it set as epsilon here. Okay, having this, we are going to okay, this is true for n bigger than or equals n, and now we are going to consider this one. Okay, we are considering this one, and what is it? When you take the LCM, you will have absolute of Sn minus S upon SNS. Okay, you will have S minus Sn, since this is absolute term. Using the symmetry, I may write this way. Okay, and this is going to be less than or equals, or simply equals. Actually, it is equals absolute of Sn minus S upon absolute of Sn into absolute of S, and here is where the things are going to take place. What is it? It is epsilon. Okay, and what is it? 1 upon absolute of Sn is 2 times of absolute of S. Here also you have this. S is some fixed quantity, right? So if you want only epsilon here, what is the thing you must have here? You will have to multiply this by absolute of S square, and you have to divide this by 2. And when you do so, you will have it to be epsilon. That is, you have absolute of 1 upon Sn minus absolute of 1 upon S is less than epsilon, and this proves what? Limit n goes to infinity, 1 upon Sn is 1 upon S, and this completes the proof. Thank you.